Welcome to homework.
All right, we've got to draw some resonance structures. And we've got this sort of diketone carbanion structure. And pretty much what we need to know is that if you've ever got a negative charge next to a double bond, like if I had, I don't know, this structure, that I can basically always do this pattern for resonance. I turn the carbon that currently has a lone pair I turn its carbon-carbon bond into a double bond, and then I hop the neighboring double bond onto the carbon that's 2 carbons away. And so this will give me the following. Well, it's not a carbon-carbon double bond, but we still got a double bond and it's on oxygen. So we're going to follow that same pattern here. We're going to take the carbon that has the lone pair and create a double bond between that carbon and its neighboring carbon. And then because that would create too many bonds to this carbon, that would have 5 bonds, we've got to swing the existing double bond up onto an adjacent atom. This time we're going to do it on oxygen. And then that will be, that's the arrow pushing for our resonance structure. Now this is a double bond. The double bond that previously existed is a single bond, and we get a negative charge on oxygen. All right, so that's the resonance structure that we're looking for. That's the second resonance structure down below. And, I guess we could draw that this has 3 lone pairs. Previously had 2, but that double bond became a lone pair. If that helps keep track of things for you, then by all means, draw in the lone pairs. Okay, let's work on our next resonance structure. We have some kind of thioether. Right, we've got H2C positively charged down to a sulfur, which has an ethyl group attached, and it's got 2 lone pairs. Okay. Now, this is a different sort of paradigm. This is if we've got an atom with a lone pair next to a carbon that's positively charged. So a common way you see this is when you've got, say you have OH and you have a positive charge on the carbon that it's attached to. One of the resonance structures you can show is the lone pair pushing down to form a double bond with carbon, right? Because carbon's only got 3 bonds here. It's only seeing 6 electrons. It doesn't have a full octet. If oxygen shares one of its lone pairs, all of a sudden, carbon's seeing a full octet. It's seeing, 4 electrons or half of 4 bonds, so it's neutral. Whereas oxygen will have 3 bonds in a lone pair, so it's going to be positively charged. So it's kind of like the lone pair becomes a double bond, and then the positive charge switches place with oxygen. This is the same thing we're going to do over here. This lone pair on sulfur can become a double bond. And then what's going to happen to that positive charge, do you think? Well, all of a sudden, carbon's got 2 bonds to hydrogen and a double bond, so it's perfectly happy. It is neutral, right? It's from group 4A, which means it wants to see 4 bonds, or it wants to see 2 bonds and a lone pair, right? So if either of those is the case, it'll be neutral. So now it's seeing 4 bonds. It's going to be neutral. So we're going to have CH2 with a double bond to the sulfur, which now just has 1 lone pair, and they're going to get a positive charge on the sulfur, right? Because sulfur is from group 6A. So it wants to see either 3 lone pairs or 2 lone pairs plus 2 bonds, etc., etc. It's seeing 1 lone pair and 3 bonds where it would want to see 4 bonds to be negative. So it's positively charged. You could also do the formula, 6 minus total number of electrons in lone pairs, which is 2, minus half the number of electrons in bonds it's connected to. So 2, 4, 6. That's 6 minus 2 minus 3 equals 1, or positive 1 specifically. Okay, that's about all there is to this. These are the 2 resonance structures. Or this, the one that I drew here is the additional resonance structure.